Hi class, hi everybody. So I'm very happy today to have with us Andrew. Andrew is currently working in Rust on InfluxDB, one of the startups in the area, I guess distributed startup, as we discussed. So he's also working on a lot of open source projects, and I think we'll hear about that a lot today, about Apache Data Fusion and the Apache Arrow ecosystem. And he actually serves as the Apache Data Fusion chair and the Apache Arrow. He used to be, or you are still the Apache Arrow.
Still on the board.
Exactly. He has also a long experience of several startups on the data management area. So we're very excited to have him here and learn more from your experience.
Thank you. Thank you for having me. All right. So Manos asked me today to come and talk about cloud data lakes, the open data lake or cloud warehouses or whatever. So that's what I'm going to do. This is my introduction. As Manos said, I've spent a long time in enterprise software, mostly at startups, but I've also worked at several different database companies along the way. So I can tell you a little bit about the arc, right? Where we're headed. So I currently work for Influx Data on a disaggregated storage database, which I'll explain much more about what that means over the course of the talk. And in the course, I've spent a lot of time working on these open source systems, but actually I'm mostly going to talk today about how people architect databases for the cloud, and sort of what architectural trends drove that, and then what features you see in those databases. And of course, so I'm going to start by trying to explain why this is important, specifically from an industrial perspective, money involved basically. And then I'll basically talk about where database architectures came from, where they've gone, and how this move to the cloud fits in. And then I'll talk a bunch about the technical specifics that show up in these cloud database architectures. So the first thing I wanted to show is, I don't know, this is the suggested readings, right? If you read this paper, it's called The Lakehouse, the New Generation of Open Analytics Platforms. And so it basically lays out the broad technical story of where these lake houses are coming. And if you look at it, I just wanted to point out stuff here, right? Like, if you look at this paper, it just looks like a nice normal academic paper that's kind of describing technical trends. But I think if you read it a little more carefully, you want, this is a master class if you ever want to know how to apply sort of academic research to put your competitors in like a bad place, basically. And so this is basically one competitor writing a paper more or less about others. They don't say it explicitly, but I'll explain how that works in a second. And they're basically trying to describe the arc of technology going this direction and say they're the next step, right? And they're competitors in the previous ones. So they describe the architectures as starting with these first generation systems where the data starts in basically one database. That's what the structured data thing means. And you load it into another database for analytics. That was a bunch of systems like this. I worked at Vertica. But there's a bunch of systems that basically had this. This is what is called an enterprise data warehouse, if you've seen that. Then they talk about this is basically the current sort of cloud data warehouse market with Snowflake and Redshift. And the big difference here is that instead of all the data coming from one database going to another, now it comes from database, but it also comes from various semi-structured things. And then they say, well, then there's this new thing, right, describing this paper called the Lakehouse, where avoid the extra step of having to load the data out of this lake into the database. Instead, we're going to build this thing called the cloud data. Right? They very much put themselves here, right? You'll notice this is what they say they built. They're all from Databricks. Yes, they have academic backgrounds, but they're absolutely from Databricks. So what this paper is doing, right, is basically saying, hey, the technology is evolving this way. We're here, and our major competitor, Snowflake, is the previous step. And so, and if you think I'm just making that up, yeah, so this was in Cider 2021, maybe. So just a few months later, you actually see what Databricks did. They published this blog and started. These are, by the way, fascinating ones. If you're dominating the database world. So they published the blog basically that they're 10x faster than their big competitor Snowflake, right? And this, you can guess how Snowflake responded, which is basically you guys are cheating. You benchmarks, you don't know what you're doing, and it wasn't there. And then Databricks responded back, well, yes, we did. This is all playing out in public. But I think this is my evidence show. There's a major competition going on. So that academic sort of dry looking paper is actually very, very relevant. By the way, they did something very similar here with this table format wars, which I'll talk about. This is the other paper I suggested. Right. This is basically a technical paper that describes how to use object store, which we'll talk about later in the talk, to do, basically track which files correspond to a table and transactionally update them. It came from Databricks. I actually think this is a well-written paper. The technology is actually quite good. Maybe we're ahead of the curve. It's arguably pretty technically superior to other options. However, there's an competing alternative we'll talk about in this technical paper. Actually, the last few, that's actually, roughly speaking, does the same thing as Delta Lake. But this one gained much more traction in the industry. The reason it's not, in my opinion, really superiority is actually very much because Databricks controlled that first one, right? As we'll talk, this is basically going to be where vendors are headed, right? Like who controls access to data is a very valuable proposition. Right? So this, which one do you think Snowflake did, right? Like they were absolutely backing that one and a bunch of other people because they didn't want to be tied to Databricks controlling the standard. So what happened? Databricks bought the company, basically bought the company that runs, that employed most of the iceberg people. Now, practically speaking, they control both for them. Right? And you can actually see realistically, right? Like you say, well, maybe they actually bought it for business. If you look at the numbers, that doesn't make sense at all. They reportedly paid some crazy number, maybe not $2 billion, maybe it's $1 billion. But regardless, the company they bought called Tagler had like $1 million in revenue. So that's like 1,000x multiple on million. You're lucky if you get 30. So the fact they're willing to pay a huge amount of money on top of what this company's revenue is suggests like the control of this technology is very important. And of course, now they have some story where like it doesn't matter what you pick, but really that's because they control both. So anyway, that's the drama part. Now we'll like maybe if that's interesting or not. Now we can start with actually like going into the technology and what's going on here, because it's not just about Databricks. But I thought that was it. There's more going on in these academic papers than you necessarily see sometimes. So, and interestingly, this was just from a few weeks ago. One of the VC firms published this thing. You actually see these three blocks are basically the same three figures as were shown in the academic paper 5 years ago. So they've often the same enterprise data warehouse to cloud data warehouse to enterprise data lake. And this blog post talks about what's going on. So basically, I'm going to talk about the transition from here to here and like these two things. And the rest of the time. I've done like high level stuff now, and I will talk more database. Does this make sense so far? Where we're headed, we're going to talk these two things. All right. So the beginning thing, I'm going to start the story in 1990s, which I realize not when databases started, but that's like when I started working on databases, or at least the late 90s. So that's when I'm going to start the history. So at this point, industry was basically dominated by people like Oracle and DB2. They all ran on a single machine. At that time, they were like not many computers anymore, right? The refrigerator size, they were like big servers that you put in your server warehouse. They had tightly integrated storage. And the server software basically had its own data file format. Sometimes actually directly controlled the hardware device. And it tightly coupled CPU, memory, and storage together. Like in the sense that if you wanted to expand or contract any one of those resources, you'd have to change the whole machine. That's going to come back a lot with the move to the cloud, and part of the driving reason is to break that up. Right. So then in the 2000s, this is like when I really started working. There was a rise of something so-called MPP, or shared nothing architectures. MPP stands for like massively parallel processing. Now, massive in those days is like 4 to 8 servers, right? Like, so it's not quite the same. But the idea was instead of having one single machine, you could actually, they were cheap enough that you could buy a bunch of them. The network's connectivity was fast enough that you could actually get them working together. You could run the same software on multiple machines. They could coordinate together and form a system out of a single distributed system. Which again, like this now has like been predominant in the last 20 years. So like probably this doesn't seem novel, but this was like brand new back in the day. There's a bunch of examples here. It's still, you probably, if you're in the industry, you've heard about a bunch of them. But they still basically tightly coupled CPU, memory, and storage together. And in the sense, like if you wanted to add more storage to this cluster, you had to add a whole machine that also had a bunch of memory. And they all tend to have proprietary formats as well as off the files. All right, so that's kind of where we were in 2000s. Now we can talk about the arrival of the cloud, right? So what does the cloud actually mean? Again, this might now all be like obvious to you, but this was like really different back in the day. So I think there's two real fundamental technologies that came along that influenced database architecture design. First one was object storage. And I'll explain why it was important in a second, but what it actually is I think a better word is like infinite FTP server in the sky. So practically speaking, it's like an infinite amount of storage, but it really is a big key value store, a distributed key value store. What that means from like an API perspective is you can basically give it a URL or a path, and it'll give you back a bunch of bytes. Likewise, you can store a bunch of bytes at a particular URL. You can like list the URLs you have, range lists, and you can delete. Like that's basically it. So it doesn't sound very interesting, right? Like why is this a hugely important technology? And like why do you give up? Like it doesn't have things like you can't modify the file, you can't just change arbitrary bytes in the middle of them. You have to rewrite the whole thing. So why do people give up those properties of file systems? Right? The reason they did is because these object stores had durability. So basically, you write data to it. The storage handles replicating failure, handover, cross availability, transactions, that kind of stuff. So from as a database designer's perspective, right? Maybe from a database system, it's very important when you put data in, right? The data is durable; it doesn't like get lost on failure. And so the fact that these things have durability built in is huge. And it very much drove a shift to bring storage out of the database, which we'll talk about. They were also, you effectively have infinite scale, right? Like you don't have to pre-provision or tell the cloud providers how much data you're going to put in there. You just put data in and they charge you as you go, which I'll explain why that's. They're also cheap, and I say cheap, relatively speaking. 15 years ago when this started, they were very, very cheap. They're maybe less cheap now than they were, but to give you some cost $23 per terabyte per month to store data. So that's 10 years ago, that was super cheap. Now maybe that's not as cheap. You can buy a terabyte drive for like $100, but we'll get there. And then the other interesting thing about this is you pay per access. You don't pay like per byte fetched. You pay per access. So whether you fetch a single kilobyte off the thing or whether you fetch like 10 megas, you pay the same cost. And the current request cost is 40 cents per million requests. So basically, this basically makes it really, really compelling database perspective to outsource your persistent storage to object store. And that's a major driver. It's cheap, it's durable, and you don't need to simplify a lot. Before we go into too much about like what actually happened, I also want to talk about there's definitely downsides to object storage, and this also drives most of the architectural things you see in these disaggregated systems. First is the latency. So the time to access the data that's stored here is actually very typically high. So it's like it's like 100 milliseconds maybe on average. These are violin plots. This is a great paper if you want to read much more about actual metrics on modern object storage. But these are violin plots. And the way you read them is this is 50 percentile. These are the 25th and 75th percentile. And so this is giving you some sense of what the distribution of the latencies are. And so this is like, to fetch 4 megabytes after you fetch it a couple of times, it shows the distribution of the latency it takes. You can see from the plots, like average latency for 4 megabytes, right? Like this one is 175 milliseconds. So that means like sometimes it'll come back a lot faster, sometimes it'll come back a lot slower. And it's actually very, very, very. And also if you do the math, throughput on here is not very high either. It's tens of megabytes a second at most. So that will drive a bunch of the key features we'll see shortly. The other thing is not only is the latency variable, the variability, of course, varies over time. So they have some great charts in the same paper that show the variability changing over time. This is classic when you have multi-tenant system, right? Like there's both some sort of monthly cycle and also daily cycles, right? Like, when Europe wakes up or when America wakes up, stuff gets slower. So again, like if you care about latency or predictability, these are things you have to worry about. Yes.
Andrew, in the previous spots, what was going on with the first byte versus like total bytes afterwards?
Yeah, so what they're doing is they're measuring here, like these are all streaming systems. So you make a request to get a particular object back, and then the system will take a while and then start sending you data. So the first byte latency is like how long it takes to give you any data back, and then the total is how long it takes to send the whole to get the entire byte back.
Okay, that makes sense.
And so that's why you see much less variability, right? Like when there's 1K, like the variability between first byte and total is much lower because as soon as you get the first data, versus it's much higher for the bigger. That's a great paper, by the way. I'll talk about that later. Yeah. So anyway, there's also variability according to the day. Another thing that it turns out, this is the chart. I couldn't believe this, so I went and double checked all this. This is the price chart per S3, right? So like when we started, you saw this like basically exponential curve price drop, and then it literally hasn't changed for 10 years.
What happened in 2015?
Yeah. Well, like why did they? Well, yeah. So the question is, why is it flat? variety of theories, right, ranging from the catalysts to either they added more features or what it is. But I mean, hardware technology has evolved significantly in the last 10 years. So the delta between what you can get on cloud and what you can get locally is significant. And that's why I think you see a lot of renewed interest in like local SSDs or like that's called edge computing, which is just a fancy way of saying back like running local machines rather than the cloud. Yeah, so anyway, that's something else. So the other major thing that was driving the move to the cloud, there's object storage. The other major technology is elastic compute, which sounds boring, but it basically is like you rent VMs by the hour. So what that means is, and I'll explain, like this probably, again, it feels like obvious to everyone here. We've seen it now, but what it means is like, if you want a machine and I start it at some particular time, I did it for some example here on EC2, and you stop at 3 hours, 25 minutes, and 24 seconds later, you pay basically for 3 hours, 25 minutes, and 24 seconds. You don't have to like pay any upfront costs. You don't have to tell them upfront how much you're going to use. And again, why was that really important? So here's a personal anecdote of the alternative, right? So this is what we used to do at Vertigo when we wanted like a new test cluster. When we, because we had these parallel machines, we have to buy, like you really have to buy physical rack. We didn't have enough money to buy this many, but like this is this type of server we bought. It's called the L380. But like to get it was a 6-month affair because you had to like budget several $100,000. You had to get the board to approve that. And you had to actually buy it. And you have to physically install them in the racks, make sure there's enough heating and cooling. We ran out of that at some point. Right. Then you could finally get going. So the difference between that and just like pushing a button and having a server 30 seconds later is like it makes a huge difference and it drove a much more architecture. Of course, the downside of this is actually super easy to spend money in this way. When we had to buy servers up front, like there were a whole bunch of capital cost controls, like we had to justify the board why we needed it, for example. Whereas here, you can basically just start new servers whenever. And it's very common to start really slow. And at least in one, possibly two startups that worked out, got to the point where like we're spending $1 million a month, like $1 million a month on Amazon bills, and you ask why, right? There's no real good. It's basically because then you spend several months trying to figure out whether everyone's spending money. That's very common. The other thing that it turns out that's really common is these machines are actually much crappier. Like they were really crappy for a while, then they got better relative to what you get locally. Now I'd say they're pretty crappy compared to what you can get locally again. And just as an example, I was playing around with this TPCH data generator thing. If you want, I had a great time. But it basically IO limited. It's tuple limited on my laptop. So I was trying to rent a cloud server that I could show this thing actually like doing even better. But I got the VM that had 4 local SSDs, and I put them all on like RAID 0, and it turned out I could get less throughput than I could get on my like year-old laptop. So, like it's a real thing, real thing. Which actually this also showed up. Yeah, so a gigabyte on my local laptop, and which is from 2003 for safety. All right, so with those two major technical drivers, right, the object store and the rental of compute, you saw a rise in these cloud databases, but really what they are is, I think, technically you call them disaggregated storage models. And I'll show you what that means now in particular. So this is a version of my picture from earlier in the talk. Right? So instead of having the CPU and memory tightly bound with the storage, instead in this model, what you have is you basically outsourced all the durable storage to object store. Right? So that's the storage of the system with an object store. And then you have an elastically scalable processing plane, which basically means that you need capacity, if you don't need capacity, you can add more machines and subtract more machines. Right? So that's exactly driven by the fact that this is really cheap and durable. The system doesn't have to worry about that anymore. And then as you need capacity, you can scale it out and scale it back without having to do capacity planning. And almost all of them have this catalog thing, which I'll talk about in a second to help you find the data on it. So that's basically when people talk about disaggregated storage models, that's what it means to put everything on object store. So we're also moving, we're going to talk about cloud data lakes. We'll get there eventually. So if you go back to this picture, this is the predominant architecture, I'd say, of production systems today. One of the big differences is it does use object store, but they don't necessarily share the same. The storage is on some global object store, but it's not shareable across systems. So it's like you put your data into Snowflake, for example, or Databricks there. And yes, it's on S3, but you can't access it. So the rise of data lake promises, instead of being in a format that's proprietary and custom database, instead it'll be common architecture or a common format that all the different data systems can read, and then you'll end up with a constellation of systems around. So you'll have specialized engines that do whatever particular task. You can have your one that focuses on time series, for example, the one that does big analytics, one that does graphs or whatever, and they can all share the same data. So when people talk about cloud data lakes, open data lakes, this is basically what they're talking about. All the data lives in a format on object store that multiple systems can access. All right, makes sense so far. So those are like the high-level architectural patterns. And I think now I'll just go through very common features you find, like architectural features you find in these disaggregated systems, largely driven exactly by the fact that you have some of the downsides of object store. So the very first thing you almost always find in these systems, certainly ones that care about latency, is you have a metadata catalog or store, depending on the system, we'll call it something different. But basically the idea is, if all your durable storage is stored in object store, but it takes you tens or hundreds of milliseconds to access anything there. If you want to do fast planning or figure out what the tables are, that sort of stuff, you almost always have some cache locally, and often it's more than just a cache. So you have basically information on where to find the data on object store. So the actual data lives here, but the information about what it is lives somewhere else in the MiDAS store. And so, like, if a user request comes in to your compute layer, the very first thing you do is you consult catalog, metadata store, whatever you want to call it. Like, what files should I be in, what tables, you plan your query, like that information, you're right. And then when you figure out what to do, then you go to object store. So that catalog thing shows up in almost all these systems. Very popular options are, you basically end up using another transaction database. The analytic database actually have another database embedded inside them to handle the catalog information. So Foundation DB is a popular choice. That's a distributed basically key value store. Postgres or other actually old school transaction systems are common as well. And so the kinds of stuff you see in these metadata systems that I've hinted, like schema information about what tables exist, that kind of stuff. Also information about like how data is distributed across the files for partitioning, obviously exactly what files there are. And then sometimes depending on your system and your needs, you'll see additional information for helping identify quickly which files to skip. So that's often used in the form of like minimum and maximum values for certain columns, which are known in the literature as small material aggregates. I think Oracle calls them zone maps. So if you hear people talk about that, that's just a fancy way typically of saying min-max values. Sometimes you'll see bloom filters and various other, sophisticated things. These metadata stores. All right, so that's one. We got a metadata store. Another property that almost all these databases have, right? Because they go to the cloud. One of the things they're going to try to take advantage of is scalable. The fact that you can expand and contract machines on demand. So that means they almost always break the different operations that are into tiers of machines that can scale independently. You almost always will see write and query, for example, separated, and then there's very often a reorganization here that comes along too, which I'll talk about. So for example, right, if here's like the schematic version of your disaggregated storage, where you've got a disaggregated database where you've stored all your state, either object store or the catalog, metadata catalog. In this case, I've got two green things handling the ingest load, right? Like writes come in and those make new files. I'll talk more about that later. You've got a query worker and you've got something running around cleaning up. If, for example, like we often see in Influx's use cases where like a UAV, right, lands and all of a sudden like dumps a whole bunch of data into your system, telemetry data, that means your workload is very spiky, right? So when these systems have the nice property that if your workload spikes, right, you can just scale up the ingest workers, for example, right? And maybe you also add something to the back factor thing, which we'll talk about later. But you didn't have to worry about scaling object store, right? Because that's handled by your cloud provider. And if your query workload hasn't changed, you don't have to scale that up either. Right? So and then when you're done, you can scale it back down. So that's a very common property. You use disaggregated storage model. It's probably one of the major reasons why you go to them in the first place. Another thing you see that's super common, which again, hopefully this is like obvious, but if you thought about it for 5 minutes, you probably come to the same conclusion. But given the fact that every object store access, both you pay for it directly and it has significant latency, right? Latency both read and write. That means almost anyone who cares about latency will put or cost, where you have lots of small writes, you put some sort of buffering in front of the write path, right? So you're not just taking data directly from the customer and dropping it into object store, you like buffer it either in memory or somewhere else first. So, for example, write comes in, you have this memory buffer, and then at some point in time in the future, you'll eventually write, it to probably in some other format to object. Probably not earth shattering. Sometimes there's a variation here where you use memory depending on the system you're running in. They might have local disks as well, local memories where you buffer stuff too. Right, it's on your store. Now the question is what challenges come along with that though? One of the challenges is if you outsource the durability to the object store, right? Basically the whole story of how your data system might move data is because you bring it to the object store. If now you're buffering data before you write it to the object store, right? You've got to somehow talk about the failure modes of that buffer and do something about it. So that adding, there's a bunch of different trade-offs people will do here. Like they'll either have their own like another write-ahead law, or they'll just accept some additional potential loss, or they'll have an extra level redundancy or something. And the other challenge with this system, right, is because you've got the read and write to your split, and then mostly you're communicating through the object store. If you're buffering information before it gets to the object store, that there's a delay between when someone writes data in and when it appears in query results. So depending on what your use case is, you might have to do, that might be a problem, especially if it's like minutes, right? If you're buffering water-bound data. So, like for example, in Influx, we have it so our query tier knows how to talk to the write tier, get the data as soon as possible, but that adds additional complexity. Yeah, so hopefully that makes sense. I'm just trying to basically enumerate like the common patterns I've seen in these systems rather than say that there's one way to do it, because that's so another common pattern you see in these, right? Again, driven by the fact that you have object store and you can't modify the storage, is when you want to delete, but you probably want to delete data or at least get it out. So what people typically do is, since you can't modify this stuff directly, what they'll do is they'll actually model deletes as additional data, right? So a delete actually writes additional things in rather than actually. So in this case, right, you send a delete and it writes what's typically called a tombstone. Exactly what's in there is I'll talk about a little bit in a second. So what you do is you write that, and then on query time, the query workers know to read the data plus any tombstones and combine them correctly and return that to the user. So in this case, right, the little white bar over there is meant to represent there's like some rows that got deleted, and so that got applied only in query time. So that's the very common thing to do. One question though is, well, all right. Now I've seen at least two variations of how people model delete vectors. Actually, we were just talking. I don't think I've seen an academic treatment apply it. Which one's better? But the first one is really common. We use it in Vertica. It's used in Iceberg. And what it means is that you go and you look at all your different storage systems, or you're trying to delete certain rows that match a predicate, where user ID equals 5. So what these systems will do is actually go look for that value in all the different storage files, find rows, the relative rows that matched, and record basically the position within the file that was deleted. Right. So that's actually a super time-consuming process, especially if you've got large amounts of historical data. But then once you run the queries, it's very easy to apply with the vectors. So that's what a delete vector is. It's the rows offsets that were deleted. The other thing I've seen people do, we did this in early versions of Influx 3, is you store the predicate. So like instead of actually looking at what rows got deleted, you just store a note in your metadata catalog that every row that user ID 5 is supposed to be deleted. And then on query time, you just add that predicate to all the existing predicates. And then
you have to store some sort of timestamp.
Yeah, well, yes, you do. And that's so one of the challenges with either of the approaches is as you add more data, right now you've deleted data, if you want to provide, for example, a snapshot consistency, so like there's a consistent view of the data at a particular time, you have to track the relative time of when the deletes came in, the inserts came in, depending on the constraints of your system, like how you do that and how complicated it gets. Tricky. Performance is also like deletes typically make things worse, right? You delete data and then queries get slower because now you've got to filter out the stuff. And of course, they don't actually reclaim storage. So not only do you get, if you delete a bunch of your data, you didn't actually delete anything, you just add a whole bunch more. So you actually ever want to reclaim the storage, or you want, for compliance reasons, for example, to like actually remove the data from your system, you have to do something different. Just a second. All right, so the next. So another thing you see almost always is some sort of data layout optimization is what I'm calling it, but compaction and reorganization is the garbage collection is used in many papers that describe this. And the basic idea is, like, if you think about what I've been talking about, as new data comes in, right, you continually write new stuff into the object store. So over time, you just accumulate lots and lots of things. You can end up spending a lot of money on it. And so what you have to do over time is, like, let's say we wrote one new little file. Well, you'll have typically some other process running around that organizes them, maybe combines them into fewer, larger files that maybe are better compressed, and maybe actually remove rows that were deleted. Yeah, and then then eventually you can reclaim the storage from the old ones. So that's that process of never, because you can't modify the existing ones, right? Given the underlying constraints of object storage, you write new ones and then switch it around. We'll talk more about exactly how that works. A little bit. Yes, let's talk about table formats briefly. Yes, so actually, the other thing I wanted to point out is, like, this slide, this process, the nice thing about these disaggregated storage model architectures is that this stuff is often happening on, like, some other set of machines, right? So, like, the fact that you can, like, start a machine and it can do the stuff in the background, it doesn't impact query and it doesn't impact write is actually very nice. It's very different than, like, for example, if you've got a local LSM, oftentimes you have this trade-off where, like, your write throughput is impacted by how fast you can do garbage collection, right? Or how fast you can merge the old other trees. Whereas in this system, it's typically not the case because the merging is happening on some other hardware that's decorated. All right, so table formats. Let's talk about table formats. There's 3 primary table formats that I know about. This is, these are the 3 big ones. I already told you which one I think is winning in terms of which one I think will get the broadest industry adoption. Apache Hudi is another one that I haven't heard a lot about recently. But basically, the idea is, the architecture I've already described, you put all your data on object store, but you have to have this, like, metadata storage somewhere to actually interpret what is in there. Even if, like, you put your data in open files on object store open formats, you still need some extra information that's probably not available to other systems in order to interpret what it is. And so that's the role these things built. So they basically let you define with another file on object store, basically, which files make up your table. So in this case, yeah, basically fancy way of, it's yet another way of keeping data and metadata separate. In this case, there's a picture from the Iceberg website. This is just trying to say you can keep data separate. If you've ever seen this icon, this is for Apache Orc. That's one file format. This is for Apache Parquet. The idea is you have data in one set of files and you have metadata in another set of, data in one set of objects, metadata in another set of objects. And so the way, like, this is the scheme the paper describes. Iceberg is a little more complicated. But the idea is, right, if you've got your 3 files on object store that make up the table, how do you figure out that it's those 3 and not something else? Well, you write, yet another file over here and purposely name this thing 001 for reasons I'll tell you in a moment. So when queries come in, what will happen is the query node will actually look at that node on the left, like the metadata pointer, basically, and that thing contains, in various formats, pointers to the other 3 files. Right? This is like a classic solving the problem with linear indirection, where now you have to do 2 access to the object store because you need the metadata thing and then the actual data, but you can get a consistent snapshot. And as long as you can guarantee that, like, everyone agrees on what these things are and that there's some transactional way to update the pointer there, that you can then build a transaction system. The way people did it, which I don't know, it's kind of cool. It's kind of I'll show with an example. So let's say you added a new file and you want to delete the 2 middle ones. So you'd write a new file, all ongoing queries, everything's fine, everything's reading, no problems. And you want to update. Typically, what they'll do is you'll write a new file with the new pointers, and you'll leave the old ones uncollected. I purposely drew this one with like these names are actually really important, and the reason they're important is because of the transactional semantics of object store. So what you need to do is, if you have, like, in order to provide transactions, if you have multiple writers at the same time, you need to, like, know which one won, and you can't have that ambiguity. You can't have disagreements on who is the writer that completed. And so object store updates are not atomic. So, like, if you just tried to update the contents of 001, we have 2 people trying to write that at the same time. Both could think they updated it, but only one of them would be seen. So instead, with these object stores, typically they don't provide any atomic updates for existing keys, but now they all provide you can write an object if it doesn't already exist, and it'll error if it already does. So that ends up being like the mechanism. So as long as basically all the writers can agree on what the next transaction ID is going to be, they can all race to try to put something into that file. Whichever one completes first is the one that actually successfully committed. And so they use the fact that all these object stores have like ordered, that the keys are ordered, right? So in Amazon, like, you can basically list all the keys, and so you know which one's the current highest one. So you try to write to the next. And if you can write, I mean, it's great if it turns out that when you try to write, someone else already wrote it, you can then try this thing again. So that's the high level way people build transaction system on top of object stores. Up until very recently, Amazon S3 did not support that particular method. In fact, if you read the Delta Lake paper, they talk about that a little bit. They say they had to build some separate service to basically manage that atomic update. Okay, so it actually turns out Iceberg, as I was talking, doesn't actually do just one level of indirection. There's like 3 levels of indirection, which I'm not, in my opinions about whether this was necessary, but I don't think it's. But the way it works, here's the metadata file that I was describing, but instead of that having pointers directly to underlying data files on disk, or like the actual data files, it actually has pointers to manifest list files. The manifest list files themselves actually lists of files, and then those are the actual list. I'm sure there's reasons for this, but I definitely makes it much more complicated than Iceberg for sure. It also means, by the way, to access any of these files, you might have to go access a whole bunch of individual objects. So, which actually makes the next topic we're going to talk about.
Sorry, is this maybe because they expect that they're going to have a high number of files, and then they want the indexing to be fast and sensitive?
Yes, I think that's right. It's like if each one of the contents of these things is large, right? Either it's because of a large number of files, or in Iceberg case, you can actually put a bunch of metadata in here, like Bloom filters, for example, which are significant in size. That if you put everything in here, this thing becomes huge, and it means anytime you mess up the way they've got it here too, you can actually you can write these things potentially in parallel, and then you don't have to rewrite them if you fail to if your transaction has to try again. But that's kind of hand wavy. I'm not an Iceberg expert, at least not yet. But yeah, is there a question?
No, I thought this was something.
Yeah. All right. So the final, I was hinting at this, right? Like I started to talk about objects, an object store, and one of the major things I was talking about was how unpredictable the latency was. It's potentially very slow, and you don't know when. In some ways, this magnifies the problem, right? Because now to actually access data, you've got to go do several object store accesses, so what people do, one surprise, probably everyone in here, that what you do is you put a cache in front of it. So this is basically something that you see in every single one of these distributed databases that I've seen, except that there's certain, if you really don't care about latency, like all you're doing is like some sort of batch workload, like generating reports every hour or something, maybe you don't have one of these, but almost everyone has. The reason is because, as I mentioned, the object store access is very high latency, and you pay per access. As soon as you start accessing the same thing a couple of times, it starts making much more sense to cache it. We'll talk about how the cache works in a second. So exactly what's in here, I'll talk about some of the options that I've seen. But at a high level, you should stick a cache between the object store and the computer. The fact that object store you can't modify stuff individually makes the cache coherence protocols typically much simpler, because you just have to basically know the last update time of each keywords. These are slides, by the way, from one of the grad students I work with at Wisconsin-Madison named Zhengping, who's phenomenal, who's doing a bunch of cool stuff. So you're going to put a cache. So how does the cache actually get implemented? I've seen several patterns. These are pictures out of this paper we wrote first citer here. So basically, one possibility, this is the simplest one to implement, is that you just literally use like the local memory on your compute nodes, right? Like you saw these compute nodes that were getting expanded and contracted in my previous pictures. So one example thing you can do is you can literally just use the local memory and disk of those machines as the cache, right? So when Instead of going to fetch data from object store, you first check whether it's locally available. Makes sense. And this is very simple to implement. We have in MiDAS, but it's got a couple of downsides, right? Like the first downside is when you bring a new compute node on, it has nothing in its cache if you don't do anything else. And so that basically means you have a big cache miss rate for newly started nodes. And the other, which might or might not be okay, depending on your use case and how frequently you change the cluster size. The other thing this does is you can think about the effective cache size here. It's basically limited to how much you can fit in a single machine. Right? Basically, because they're not coordinating, if each query, each one of these compute nodes sees the same workload or is accessing the same object are going to be in the cache multiple times, right? On one individual machine. And so that means that the amount of like total volume of data you can cache across your cluster is limited to what each individual machine can do. But this is super simple. It's probably what people implement first. So a more sophisticated thing that you see people start doing is they still keep the cache on the different compute nodes, but this time instead of each one acting entirely independently, they coordinate amongst themselves, basically form some sort of distributed machine, or right hinting they agree. So like classic schemes here is you do partition, you do like consistent hashing or something, so all of those agree on what object should be in what machine. And so when a particular machine needs an object from object store, it goes and checks the compute node that's supposed to hold it. This is, for example, the scheme that Snowflake uses, or at least the one that one of the papers we read that talks about this. As you add more machines, it has a store. But of course, this gets more complicated because now you've got cross compute zone interactions, and they're no longer stateless. So scaling them up and down becomes potentially more challenging. You want to pre-warm the cache, for example. Now you have to wait for it to actually be warmed up before you can add it to the node, which delays how fast you. The other thing that I think you see more of, this is like even like taking it to the next level, is you'll actually see a whole separate layer of cache nodes, right? So rather than just have them be part of the compute nodes, which if you put them in the compute nodes, now they're tied to like the cache size is tied to how many compute nodes you have. You can also pull it so it's in its own layer. Now you have your own distributed system, like another distributed system now to worry about. But depending on your use case, maybe that's like actually Influx has a version of this for some of its things. Yeah. So the other thing you can do with these, and I just want to preview like some of the stuff I think Ping's working on, is you normally think of a cache as just caching the bytes, right? Like object store returns bytes, and then the system has to interpret what's in those bytes. But if you have a machine that you're using for cache that has a bunch of CPU already, nothing saying you have to just cache those bytes, right? If you can make it work with the query system, you can cache other things. This is especially, I think, interesting when the data, if you can optimize the system end to end, like whatever the storage format is, and your query engine, that's great. You can always change how stuff's stored. If you don't really have control of the storage format, which is increasingly common with these open data lakes, right? You're just going to be reading Parquet files. You don't control that. But if you want to improve performance, one way to do it is you put your special sauce in the cache node itself, right? Like when you read off this, you guys prepare it in some way for better querying, depending on what your system. So that's an example of what this. So that's what this project is all about. Basically a system that's running queries against Parquet files and object store, but instead of actually touching the Parquet files, typically the system will read the Parquet file and actually transcode it into a efficient form. Using some sort of like every other query stuff. And then you have the query engines and the caching layer working together. So basically what happens is the predicates get pushed from the query engine to the cache. And of course, there's also some interesting questions there about how much do you do when you overload the cache. But there's a
so this is like you have your own optimized layout, for example, for your query engine, and you store this in your cache.
Absolutely.
Yeah.
Yes, that's exactly right. And you might have Parquet is great for a lot of reasons, but if you look on the internet, you'll find lots of people identifying challenges with the format, not the least which was that codings were designed 15 years ago. So they're not really able to take full advantage of modern CPU processing. So there's like a bunch of faster, better encodings that people have invented since then. But because the standard moves relatively slowly, that they haven't been incorporated widely into the format yet. But with a system like this, you can manage it. And this is some great results he has. Won't surprise you, it's both better memory and performance, but you can read the paper and working on it. So I think finally to wrap up, I'll talk a little about the future directions that I think things are headed. So the first thing is, you probably could guess this, given what I've been talking about. I think this open data lake thing is actually where the industry's headed, but it's actually good, which is, it's a fancy way of saying instead of putting it in proprietary files on object store, we're going to put all the data in open files. I think it actually opens up a huge amount of opportunities. Part of the reason is because part of the reason why database companies have been super valuable in the past, probably still in the future, is because once you put your data in there, there's a huge gravity to get it out. So it's not like it's locked in there specifically, like actually get it out. But realistically, like especially in the cloud environment, you literally have to pay to copy the data somewhere else. So what that practically means is a huge data gravity. So once you put your data into some particular vendor system, it's very likely that it stays there and you continue to pay that vendor. Even if another system would have done a better choice for some particular workload. And so I think one of the promises of this design is that stickiness, and that actually disincentivizes, it limits innovation. That's like now if you have a specialized engine that would do some kind of query much faster, better, cheaper, whatever, but the data lives in another system, like customers can't use it. This I think has the real possibility of actually allowing people to use their big enterprise data warehouse systems, but then can actually use a bunch of interesting startup, or other technologies because the data is in these other formats. Yeah.
Is it also now this creating maybe a gravity towards not innovating on the formats? Because how many formats going to have, right?
Yeah. So the question is, if all the data ends up looking like this, right? This is I'm very much not an unbiased. I'm giving you a non-unbiased view, biased view of what I think is the important formats, right? But these are the ones I work with closely. So people say Orc should be up there. People say Delta, right, should be up there, but it's probably Parquet. Like there's very real criticisms of Parquet. There's better things than Parquet for much difference. And I think there's several interesting startups that are trying to come up with whatever the next version of Parquet is. I think it's a tough business because Parquet is so widely adopted across the industry and tools, and it's open and it's business super well understood. And there's also huge amounts of data already existing in that format. Like the barrier to doing, like you have to be probably 10x better in a couple of dimensions to replace it. Maybe we'll get there with these alternative formats, but I haven't seen one that's 10x better. But what I do think there's all sorts of opportunities, even if the data lives there in Parquet or whatever, that doesn't mean you have to actively query it. But as you fetch the data, you can do things like part of the things do in Parquet. But if this really comes to pass, I think that could be a major game changer for the data architectures and business models. But of course, I started the talk. You can see how important this is to people who want to be the next data platform, right? Like Databricks or Snowflake. Like they very much want to be able to control what this layer looks like, because it's been the traditional key to unlocking data with company value. The other crazy thing that I think maybe we'll see is further disaggregation, right? Like, so in a lot of ways, I started to talk with the systems had combined memory, storage, and CPU all on the same machine, right? And then Advent of Object Store basically pulled the storage away from the CPU and memory, but the CPU and memory are still basically tied together. You rent the machine from Amazon, you still get EC2, from EC2, you still get memory and CPU, and they're tightly bound. You want more CPU. But without no memory, I guess you can do different instance types, but you still need to get them in package.
But so do you see this in the context of serverless or also of?
Yeah, I think serverless is part of it.
Yeah.
Like I'm talking more broadly, right? If you think about database architectures in general, where the storage has now been disaggregated from the CPU and compute, I think it's very reasonable to ask, why not disaggregate the compute and the memory, right? Or at least do some versions of that. And so I think serverless is one. This is some crazy slide. I'm sorry, there's lots of things on it. You might imagine, right, from my previous slide, you stick another layer in here, right? Now you've got disaggregated memory, storage, and CPU are different, and you can scale each of these independently. And in this case, if you really pull most of the memory storage away from the CPU, running this kind of stuff on server, like Amazon's Lambda. That becomes maybe far more compelling. Whereas today you run stuff on Lambda and it has to pull data off object store. It's going to be really slow because you got to fetch all the data and stuff. Versus if you had this memory stuff, maybe using Lambda is a far more compelling idea, right? Maybe that would be a disaggregated CPU memory storage. You can, another way to.
So I know this is conceptual, but it's more of a prediction with not all the details figured out. But how do you envision this memory layer? I mean, is it going to be probably another like a memory server, or it's going to have some local CPU as well?
Yeah, I think so.
Yeah.
Like that's one option. In fact, that's basically liquid
Right,
cache is one version of that. Another option is it could be like RDMA. I know there's some fancy new version of CXL. I can't remember what it is, but basically remote memory, so that you don't actually have CPU. It's not like you have a separate server with a bunch of RAM. You actually have some remote memory that your existing servers just access over memory. I don't know of any like commercial product that uses RDMA for cloud deployments. There's a bunch of work, especially at like the Chinese internet companies. I think there was a paper in Sigma this year about for databases that are hosted where they kind of they're providing a service. There's papers that describe using RDMA to do disaggregated memory systems, but I wouldn't say those are you could run those yourselves, right? They're part of some service that's that was my feeling. So we'll see. I think that pulling the cache out is far more practical. Like it still has CPU, but not as much. It's just more
Right. Yeah.
I think that's basically what I got. Yeah. Thank you very much. I hope that's entertaining.
Any questions?
For Amazon Lambda, why hasn't it able to access local storage? Why does it have to connect to cloud?
So if the question is why does Amazon Lambda have to connect to local, doesn't have local storage? So my understanding of what Amazon Lambda is, and maybe I might not fully understand it, is it's basically they run a fleet of machines that can run VMs for you, and they handle Docker containers for you. And so they basically handle getting it in place. And so when you run a Lambda, it basically starts a new Docker container for you. It has no local storage. Like it might have local attached disk, but as soon as it's done, the local storage goes away. So what that means is yes, you can scale out millions of container images running, but as soon as they go away, they lose all their state. Yeah.
Is the primary assumption of the memory layer that the benefits of the cache will outweigh the instability and latency? Is that the?
You mean why not just read everything directly from object store?
Yeah. Is that sort of what the point is?
Yeah. The point is those the caches that I was showing are running in basically the same cluster. So with that, they're running close to the machines that have the CPU that are doing the compute work. So rather than have to go talk to some, in some ways, right? It's all probably running in some giant data center, in the same data center. But it means that your nodes are kind of talking to a fast network. Rather than to access storage in S3, you have to go talk to an API server, and goes talk to their data servers, blah, 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 and eventually comes back. So from your application's perspective, accessing a VM that you control as you put in your local virtual network, way faster and way higher bandwidth than any arbitrary, just fetching some arbitrary request to object store. But you can see even some of that starting to change, where the cloud providers are offering different tiers of these storage systems, right? Because they recognize some applications just really care about cost. Right? Some applications really backup maybe, for example, whereas some applications really care about low latency, like real-time query. And so they'll actually offer different tiers of object storage. They still have the same APIs, but maybe have different restrictions. So there's something called S3 Express, I believe is what one zone, I don't know what the marketing term was. But it basically means they put the storage closer to the compute and they run an SSD. Well, I don't think they publicly talked about the difference, but basically everyone assumes that what S3 currently runs on is a whole bunch of spinning disks, right? Drives. And then this S3 Express one zone, blah, blah, blah thing, it's basically SSDs that are closer. So that consequently means it's much lower latency, much more predictable, but they also charge you more. And then it's actually also there's a bunch of like restrictions on which availability zone you can move in and where the data can move. So I haven't seen that used that much in practice. Maybe I just haven't heard, but I don't think that's common because it puts a whole bunch more restrictions on how you can deploy your systems in these.
So,
Yeah,
go ahead. You have a question.
and this might have been covered a bit, but you were saying that we want to use an open data format because that would allow us to migrate data between different systems. But wouldn't that mean that we're losing the benefits of using a data format that works particularly well for whatever we?
Yes, yeah, I mean, that's exactly the trade-off that people point out, right? Is that if you use an open data format, you're basically stuck with whatever is in that format. And yes, you know, and if you had the full freedom in engineering to design a system that was more optimal for your particular use case, yeah, you'd probably go faster. So in some ways, that's like this liquid cache idea is you're trying to get the best of both worlds, right? You use a specialized format, but that's not going to be the format of record. And then there's other people who are actively trying to add new stuff to file formats. But yes, like that is a fundamental trade-off. And the question then becomes too, like, also you'll hear my pragmatic voice coming out now is if you, in theory, right, I'm sure any of you would design something better than Parquet for some particular use case you have, right? But your ability to actually like apply enough engineering effort to get an optimized implementation that actually works as well as the existing optimized Parquet implementations, for example, I think that's a much harder proposition. Not because it's not like possible in theory, but the actual just effort required to create them is quite high. And there's been a lot of, you know, now that these are open, you can attract a bunch of contributors. And this is a lot of what I do with the open source work. You get vast swaths of humanity on the internet helping, like all chipping in, you can muster quite a lot of engineering effort. So, yeah, that's what. So yes, you can do it, but it's also very expensive. So you have to have some.
I think it's part of the whole movement from, you know, closed to open source, and then now all of a sudden you don't want. I mean, you're not going to have a closed code anyway, so you want to have something that's easy to interoperate, and it comes with trade-offs, right? So,
Absolutely.
So I have one more question. So in your projections for the future, do you see any, or where would you see, in what parts of the whole architecture would see specialized hardware or accelerators being of use? If you have any thoughts of that?
Yeah, no, I mean, like that's the kind of stuff you could put in these two layers. Even with this open format, right? Yes, it says Parquet, right? But you want to put GPUs in these layers. That's an excellent example of like a specialized processing thing. Maybe sourced even, right? You don't have to tell people what's your internal memory format is or whatever. Provide phenomenal performance for certain applications. So I think there's also, you know, there's all sorts of opportunities. Like if you don't have to own the data and deal with durability, consistency, and all that, like that already is taken care of for you. Building analytic systems on top of this, I think there's all sorts of possibilities. Especially, right, like harping some other talk, I didn't really talk about it here, but it's also another movement, not just the open data formats, but pieces of building query engines so that you don't have to build the whole thing from the ground up, right? Like if you have to build a SQL parser and a query analyzer and an execution engine and a thing, and then also apply your specialized hardware, like that's a much bigger undertaking than just the specialized hardware. Right? So maybe perhaps with the growth of those more modular systems, yeah, I think there's lots of interesting hardware stuff here.
So, I mean, especially if you have all these different layers you're using, it seems like there are a lot of distributed systems that you need to be simultaneously running to use one of these.
Yes.
So when you're making a distributed system for something like this, what are you prioritizing? Looking for speed, or are you looking for reliability?
That's, yeah, what you can. So, I mean, the real answer is it depends, right? And that's part of why there's not just like one disaggregated database architecture, right? There's a whole bunch of them and they all have different sets of trade-offs. But yeah, I mean, I think we've certainly found it, and it's, the complexity of running these things is actually quite high, right? So if you were Kubernetes, like you probably have your head under a rock not to hear about that. But that part, both made things better and worse, right? Because it actually allows you to run these sort of big complicated distributed systems. But that also means people build even more complicated distributed systems. So oftentimes you'll end up, I showed my like idealized view with like 3 different colors, right? But like realistic real systems will have like 10 or 12 different things doing different, like different operations. There are different services and they're all microservices. It looks great on paper, but it's very hard to like understand what something goes wrong, like exactly where they tell you. So yeah, I would keep it as simple as possible.
Yeah, so how do we decide which data to be stored in the cache? So is it going to be the most frequently data that is being accessed? And in that case, will the performance like increase over time? Because
Excellent question. I believe that's the topic of Zhangfeng's next paper he's working on is basically cache. So I'm not trying to be glib. It's more like when you have a cache, you have to figure out what the format is in there, but then another major piece is you have to figure out what the policy is. Like when you fetch stuff in there, when you evict things, his system has a little bit more, has even more potential options. Like you have to figure out, without going into too much detail of what the paper is, it's like got several transcoding steps. And so you don't necessarily have to transcode the whole input data to something else. You could only do a subset of it, or you could actually only do some of the phases, or maybe you run the query the first time and then in the background you can transcode some of the stuff. So I think there's a bunch of like, it's also interesting research about how those things trade off.
If I have a quick follow-up on that, so it's about liquid gas, right? And
Yeah.
the current progress that's happening there. So transcoding is essentially changing the layout of the data.
Yeah.
Right, to whatever is optimal for your query.
So in particular, he applied, like just to make it specific, there's a couple of papers that describe encoding algorithm called SSTE, which is essentially like fast string table something. But basically, it's a more modern string encoding that's Cindy friendly, and there's also something called fast lanes, which is Cindy friendly, like bit tagging and RLE algorithm. And so basically, applying those techniques to data that came out of what was originally stored in Parquet, but now it's stored in memory in those.
So yeah, that makes perfect sense. So then one quick follow-up is, would you see anything other than transcoding, like partial query results or anything else?
Yeah, there's all sorts of stuff. Yeah, you put partial query results in there, store the results in particular predicates.
Okay.
If you're running dashboards, right, you store the whole historical.
So for example, you can do a partial aggregation, and then if another query comes, it can reuse some part of that already.
Oh yeah.
And then you do whatever else new data that you have to access, right?
Yeah, that's something I don't know if you guys are like writing papers or anything, but something else I'd love to see is a practical paper about doing incremental updates to materialized views. That would be one implementation of one way of doing what MiDAS was talking about, right? It's like it's common you have a query like tell me something about the average for every half hour of the last day. Right? You think like that query basically most of it's the same, but it's only like the leading edge is different. So figuring out incrementally how to build, like keep that up to date. I feel like there's papers about it, but they're not like I couldn't just go give it to you.
Right.
But that might just be because the problem's too hard. But I think if someone wrote a paper like that, you'd see it get implemented pretty quick. That's what I'm thinking.
Any other questions? Okay, let's take our speaker again.